Okay, good. Start. So let's start by reviewing what we talked about yesterday. You said we started out with talking about QP and VP. And so if B is an integer that's not divided by P, then if you write A over B, that rational number is actually in ZP. So therefore QP is just fraction field of ZP. In fact, to take this, get this fraction field, you just need to invert P. So you don't have to invert other elements. And we went on to talk about how to solve quadratic equations, like take square root of 2, say, in Z7. The way we did that was that we first of all solved x squared congruent to 2 mod 7. That should be 304. And then when we solve the next congruent, modulo 49, we start out with the starting point where x congruent to 3 mod 7. We write 3 plus 7y and take square, and then we solve it to get a y modulo 7, and then the next one gets you to the 7 cubed and go on. That gives you eventually a 7 additive number. You can't kind of really write it down explicitly. There's no pattern to place, but you know it exists. And then a generalization of all this argument is a tensor lemma. Namely, if you have a polynomial, maybe I should say a polynomial fx in ZP coefficient and takes reduction f bar, and then suppose that this f bar has a simple zero, then we can lift this simple zero uniquely to a alpha in ZP. I don't have a penalty. Alpha belongs to ZP. Such that this alpha is congruent to the alpha bar you started out with modulo P. And then using this, we talk about the structure, the group structure of QP cross. The way you do that is first we split off the P power, that's going to give you a Z. And then the rest will be those P-added integers which are not divisible by P. It turns out those are invertible by sort of the same argument as how you show that the integers not divisible by P are invertible. And then ZP cross, is take modulo P, get to Z mod P cross. And then this one has a Teichner lift back to ZP cross, so therefore we can factor out ZP cross into the product of the term reduction and those P-added integers which are common to 1 modulo P. And for those P-added integers which are common to 1 modulo P, you can take the P-added log, just use the formal Taylor expansion of the log, and you get to ZP, and going back you take exponential. To normalize better, you have to divide by P and multiply by P, whatever. And this works very well with P odd when P equals 2. I didn't say, but I'm just going to say it now. The first isomorphism is still 2. The second one, the Z mod 2Z cross is 1 element. No. So you want, instead of doing Z mod 2Z cross, you do Z mod 4Z cross. So there are 1 and negative 1, or 1 or 3, 1 or 4. And on this side you have 1 plus 4 Z2. And you can do the log and exponential, but instead of dividing by 2, you divide by 4, and multiply by 4 when you do the exponential. You still get this isomorphism. The reason you do 4 instead of 2 is because the exponential map does not converge if you multiply by 2. So you really want this odd. So because you divide by n factorial is highly divided by 2. So when you do exponential, you really have to do 4 times instead of 2 times. So the exponential converge. That was kind of the head waving last one when I talked about it. In any case, so therefore the QP cross can be written as sort of 3 factors for P odd: Z mod PZ cross, and ZP. Now I look at those non-zero element QP divided by the squares. So this is ZP here, because P is invertible in ZP, so therefore 2ZP is just same as ZP. So the last factor does not contribute anything. The first 2 factors, each one contributed Z mod 2Z. The reason I want to study this QP cross over QP cross square is because at the end of the day, I want to understand the quaternion algebras over QP. Well, let's first of all recall that the quaternion algebra, this quaternion algebra over K, defined using the 2 invertible elements A and B. If you change the A and B by a square, the quaternion algebras are isomorphic to each other, so you don't really change the quaternion algebra up to isomorphism. So this way, we know that the quaternion algebra over QP up to isomorphism only depend on A and B in this sort of quotient, which does not belong to the finite group, Z mod 2Z and Z mod times Z mod 2Z. So last time I kind of mislead you probably. I said, okay, now I just need to check for how many cases? 4 times 4 equals 16 cases. It is a little misleading, but I need to check these 16 cases. But actually, for many of them they're isomorphic. For example, if you take AB and you take BA, they're automatically isomorphic. So in fact, we're going to show today that there are only 2 isomorphic classes. One is a matrix, the other one is a division ring. So that's the goal today. So let's go. Page 3. I'm going to talk about sort of quaternions over QP. And I'll say at the end a little bit of global compatibility. So to start, I want to take this is my gamma, like you're not. A generator of the group Z mod PZ class. So this is cyclical order P-1, just take a generator. Actually, I don't really need a generator. What I want is that I want a generator of the quotient. But I messed up, just take a generator. So the reason I want to do this is because it's too far. I want to, so this quotient, right? The first factor comes from the Z here. The other factor comes from Z mod PZ class. So I want to take a generator of this one. To write down this sort of quotient explicitly by some cosine representatives. So I want to take this reduction mod P because I will have a Teichmann lift. So I'm going to write gamma to be the Teichmann lift of this reduction mod. So it's going to be an element in ZP plus. So this way, I can pick cosine representatives. I get 1, gamma, P, and P gamma. So basically, I need to check for AB in this set here. Set. Okay. So before actually classify quaternions over QP, let us first of all do a little bit more general theory. So start with this trivial, somewhat easy lemma that if A is a square in a field, for today, whenever I say field, okay, I mean the character is not 2. I want to avoid character 2, but probably do it. It's a square, so to say. I'm just going to write A as square root of A squared, where square root of A is an element in K. Then, I'll say that as long as one of the A or B is a square, that is this quaternion algebra I defined earlier. This is just a matrix. It's long consensus. Nothing new. So proof. I'm actually going to write down the isomorphism. So this one has, two. Essentially, I want to specify where I and j goes. I and j go. And for I want to go to root of a and negative root of a. In fact, there are 2 roots of a's. One goes 1, and the other goes the other. And for j, I want to send it to 0, B, 1, 0. Okay? So you can check, easily check this is a sort of miracle matrix that J squared equals the identity matrix. That's sort of B, diagonal matrix B. I personally really enjoy it. I like this matrix very much. It's a weird matrix. Okay, so there's a little bit of a checking, a very quick checking that I want to check. I'll check it for you. You need to check that I of, let's call it phi. You need to check that phi of I, phi of j, equals negative phi of j, phi of I. Right? Because we're in a non-commutative setup. So whenever you write down a map, you really need to check that this relation on the left-hand side of the quaternions is satisfied when you map it over. So, we really need to check this. Because this is almost like a scalar, so I'll just forget about scalars. I want to check this is equal to this, up to the sign. Exactly up to that sign. If you can't see this down here, just look it on your own paper. You can do it. And I don't know, exercise. Or stare it for 10 seconds while I erase the board. Check, convince yourself this is true. So in other words, if A or B is in square, then it's just a matrix. So if you look at this list, I mean, like, you have like 16 possibilities, right? Already, I guess A or B equals 1. You know, whatever, 7 possibilities already. Those are already determined. I wanna, before giving the classification, I wanna talk about a long proposition. If A is not a square in K. I mean, when A is a square in K, we kind of know very well. I again want to know that when this is the matrix algebra. It's not done yet, of course. Everything's a matrix. So, if A is not a square X in the field K, this quaternion algebra is the same as the matrix algebra if and only if B is a norm from K adjoint root of A. Yeah. I.e., so B is a norm of an element X plus, say, Y root of A. The norm of this, so take norm, meaning that you start with X plus Y root of A times X minus root of A. Minus Y times root of A. Or rather, you can just multiply it out equals X squared minus AY squared. For some X or Y in K. And this is also even only if you look at what we require here, we require that B equals X squared minus AY squared. Somehow, and then we're somehow missing where this kind of a Delphin-Time equation that we try to solve X and Y. That satisfies this equation B equals X squared minus AY squared. It's not very sort of symmetric. There's sometimes we'll actually homogenize it. So that's equivalent to say that so BZ squared equals X squared minus AY squared has non-zero solutions in K. Here, when I say non-zero solutions, I mean a solution where X, Y, Z are not all zero. I mean, of course, any homogeneous solution, setting all variables to be 0, and you get a solution. That's pretty stupid. Right. So what we're saying is that quaternion algebra being the same as matrix algebra is the same as this B can be written as x squared minus ay squared for x, y, and k, or equivalent is homogeneous quadratic equation has non-zero solutions in type. So first of all, actually, sorry, before giving the proof, I want to say that, look here, that I put a parenthesis on this condition. A is not a square impact. The reason I put a parenthesis on this condition is that because it's not important. I mean, like, in the sense that you don't have to put this. When A is a square impact, the previous lemma I just erased says that this quaternion algebra is isomorphic to the matrix algebra. And in that case, K adjoint root of A is just K. So, of course, B is the norm from this field itself, in the sense that it's equal to element homologically true. And this one, if A is a square, then you can just take Z equals 0, and if A is a square, then X should be root of A and Y equals 1. So that's a solution. This has a non-zero solution. So I mean, both three sort of equivalent conditions are both true in that case. So that's still equivalent, but it doesn't sort of say too much. So I can post that condition or I can ignore it, either way. But when I prove, of course, I assume A is not a square. That's where the proposition has some content. So I want to first of all say that second equivalence is obvious, or it is true. Basically, if B equals, I mean, like if you have B equals, shall I just say that how this is done? I mean, like if B equals x squared minus ay squared, of course it takes z equals 1, that gives a solution. And going the other way, if b squared equals x squared minus ay squared is a non-zero solution, basically you just get 1 equals x over z squared minus a times y over z squared. So get back to the previous one. Oh, sorry, no, sorry. I have a b here. It's a little strange. Okay, you may wonder why z is non-zero. If z were non-zero, then I mean that would mean a is going to be a square, which contradicts to our expression. So, in some sense, so these two are obviously equivalent. I'm just phrasing it in a slightly different way, which I'll use next time. The first two. Okay. Maybe I'll give them the sort of one, statement 2, statement 3. I want to say that. So what we just proved was that 2 and 3 are saying. Now I want to do 2 and 1. Let's go one way. 2, 2, 1. So suppose that B can be written as x squared minus ay squared for some x, y, and k. I want to show that the quaternion algebra we constructed is a matrix. Let's use this. Oh, I don't have to erase that. I just have to change a little bit over here. That I need to check. Okay? It's a very sort of combinatorial game. To do 0, A, 1, 0. So this will guarantee that somehow phi of I squared equals A. And for whatever matrix I have over here, I need the phi of J squared to be B, right? So of course I want to use an equation that B equals x squared minus, B equals x squared minus ay squared. So whatever I write in here should kind of reflect that in column. So rather I want to use x, y, and a instead of b to put in this matrix. So if you play around with it a little bit more, a little bit. So that's the matrix we want to put in. It's not difficult at all. Play around with it. If you look so, x a1 times this one, you get x squared minus ay squared, and then I hope I got it right. And you can also check that phi of I times phi of j equals negative phi of j times phi of I. I am not going to check this. Go back and check. So 2 to 1 is easy. Just get rid of this. Going back is not that difficult either. But we need a little trick here. So here's a problem. So you start. So suppose that there is a matrix, so you get some sort of phi prime. It can be distinguished from that one. I mean, what you really want is that you want your I matrix to be mapped to the 0, A, 1, 0. So that whatever j is mapped to, you can use a relation and then get some sort of equality like E equals x squared minus ay squared. But the problem is that you don't know which matrix this I is mapped to. You have to play a little trick. So now, okay, I don't know which matrix it's mapped to, but we know that for this matrix, the square is equal to A times the identity matrix. There's a, if you learn linear algebra, there's a kind of normal form of a matrix once you know it's captured the polynomial. So I mean, somehow this captured polynomial is clear. It's x squared minus a. This is captured polynomial. So once you know the captured polynomial, there's a kind of normal form you can put it into. So I want to say that you can find a G in the matrix. I'm sorry, in GL2. Okay, such that if you conjugate your matrix, it becomes the form you want it to be, namely like that. Because this is a kind of normal form. I can give it a more explicit way. What do I mean by finding a invertible matrix to conjugate it? It means to choose a new basis. So that's the same as choosing a new basis given by, choose arbitrary E1 as a basis. And the next basis, you want it to be phi prime I times E1. So therefore, phi prime I applied to E1 will be equal to the next basis. So the first column will be 0, 1. And then phi prime I apply again, you should get back to A times E1 to get A here. The tiny basis thing is, why are they linear independent? So this can't be lambda EI. If it were equal to lambda EI, this would imply that otherwise lambda square would be equal to A. We said A is not a square, so it can't be like that. But actually, you can change your EI to be another way. Either way. So you can change it. So now you want to turn this entire isomorphism into that one. So what you do is that I want to go on to that. So I want to take phi of, I don't have a letter for quaternion, so I have a Q. It's a very terrible Q for a quaternion element. G of phi of Q, G inverse Q prime. So I define a new isomorphism. We call that, if you conjugating matrix actually define an automorphism of the sort of matrix algebra. So therefore, if you conjugate your map further by this G, you still get an isomorphism. It's again, an isomorphism of this K algebra. So we arrive at this phi here, except that I don't know what's happening here. I apologize. I go here and erase things, and you have to write things on your paper and copy everything. I'll wait a little bit. Right. So now you play this small trick, and you kind of rigidify where I should go. And now you want to understand where J is going. Such that J is going to somewhere, x, y, z, w, I have no idea. But it must satisfy this equation that phi of I, phi of j equals negative phi I dj. Now let's explore what this equality looks like. I mean, what it tells you. Still in the linear. It's 2 in the morning, so I think your brain is still working, I assume. Let's see. This is something you don't want to do in the afternoon. Okay, multiply. Minus y minus w. X is negative. So you want the corresponding entries to be the same. So what do I get? I get that y equals minus ac, and what? X equals to minus w. Right? And y equals ac and y x equals w, but then you see up here also it's like y equals negative ac, and this is also x equals minus y. Although there's 4 equations that are related to 2. So that comes from this equation over here. We'll have another one we can use, which is phi j squared equals b, meaning b times identity matrix. Oh, right, identity matrix. So spell that one. Xy is minus w minus ax. Oh, sorry. AC. And here I have zw squared. So I'm just going to do one term calculate. So equal to, I'm just going to do this term here. So what do I get? I get minus w times minus w, so w squared. Minus az times z, so minus az squared. And this should be equal to diagonal matrix bb. There we go. So we have a solution then. So we have b equals w squared minus az squared. That's it. So we find the solution. And you can check that this term is automatically 0, and this is also sort of the same thing, w squared minus az squared. So that comes because I now have a solution to b equals to w squared minus a. Okay. Yes.
So there's, if you have commuting matrices, you can simultaneously diagonalize them. These aren't very
They do not commute.
Yeah, they anti-commute, but they still stabilize the eigenspaces, don't they? Or not?
I mean, you can't. I mean, you're talking about a general field. You can't. Well, eigen spaces. The eigenvalue may not be in the field. That's a problem. Especially in this case, you see, phi squared equals a. The eigenvalues are root of a and negative root, but they're not in the field, so you can't diagonalize. If you can diagonalize everything in the matrices. Because the entire theory, because the upshot is that you can only work with Q or somehow. It's not algebraic closed field. In some sense, a version of generation of linear in that sense. Good question. Other questions? Okay. Wow. So that proves a lemma. That proves a proposition. I want to show you my notes. So now I want to the goal is to classify quaternions over QP. So I want to give some sort of notation, so that we can talk a little bit better. So for K goes Q by the reals or QP. I want to, the whole idea of the entire argument is I want to treat R and QP equal in some sense. And where I take AB to be K cross. It's called Hilbert symbol. Which is I do A comma B lowercase k to be 1 if the quaternion algebra defined by A and B is just a matrix algebra. It's -1 otherwise. So just a plus minus 1 sign. And as we see in the previous lemma, just to remind you that if the quaternion algebra is not isomorphic to the matrix algebra, that means that the equation, if you change it a little bit, move things around, it's the same as x squared equals to ay squared plus bz squared. When this is isomorphic to the matrix algebra, this one has non-zero solution. When it's not, that means this has has only zeros. So this, right now, it's just a convenient way of telling these two cases apart, whether the quaternion is isomorphic to the matrix or not. Maybe just give one quick example. So for the reals, I'm just reinterpreting what we have learned. We're just reminding you that the quaternions is the same as matrix if A is bigger than A or B is positive. It's negative if both terms are negative. And let's just sort of quickly check that this equivalence here. Let's quickly check this equivalence. When A and B are both negative, you see, you're looking at the equation x squared essentially plus y squared essentially plus z squared equals 0. By positivity, for x, y, z are real. So by positivity, for this to be 0, the only possibility is that x, y, z are both 0. All 0. Now just let length 0, which will probably take a whole board, meaning all 3 points. Theorem, I mean, we already know what this Hilbert symbol looks like when k equals r. So I'm not going to do that. I'm just going to take k equals 2p. The first thing is that